So, good morning everybody. I think we can start under these quite exceptional circumstances. Looking out of the window at where I'm living, it seems to me that the complete warning was in vain. But it was so severe yesterday that I thought we rather needed a decision, and this decision was that exceptionally we'll have this lecture as a stream only and not in the lecture hall. I hope this will be fine for you. I hope the stream quality will also be okay. And we see how we can move on. It's a pity that we can't have questions now, but as soon as we return to the lecture hall next Monday, you can ask all questions that you like on the lecture. All right. So what did we do last time? Last time we first of all talked about the Jeans theorem. And the main purpose of the Jeans theorem is that it gives us a construction principle at hand how to set up phase-space densities for stellar dynamical systems. And the idea is that we saw that integrals of the motion are also stationary solutions of the collisionless Boltzmann equation, and therefore all functions of integrals of the motions are also stationary solutions of the Boltzmann equation. And if we know from symmetries through Noether's theorems, for example, that energy or angular momentum or so are integrals of the motion, then we can set up phase-space densities by choosing arbitrary functions of integrals of the motions only. And we used this statement to construct a very simple model for a stellar dynamical system, namely the isothermal sphere. And for that we assumed that the phase-space density was only a function of the energy, not of angular momentum. So this means that in addition to spherical symmetry, we assumed that the orbits should also be isotropic. And then, well, essentially we picked an exponential function mimicking the Boltzmann distribution known from ordinary equilibrium thermodynamics, and then derived radial density, number density profiles under these conditions for the isothermal sphere. And we saw that there is a singular solution which falls off with a radius like 1 over radius squared. And there is also a non-singular solution that reaches a finite density in the core. All right, this is a simple solution. It has the fundamental advantage that it reproduces the flat rotation curves in observed galaxies, but it has the fundamental disadvantage that its mass is infinite. All right, then we talked about stability in self-gravitating systems, and we saw that there are many reasons to think that self-gravitating systems cannot be stable. One reason derives directly from the virial theorem, from the minus sign in the virial theorem, which tells us that self-gravitating systems have a negative heat capacity, and because they do, the inevitable energy loss in these systems, for example by the loss of particles, leads to shrinking, and this shrinking leads to heating up the remaining stellar dynamical system. So this means that stellar dynamical systems or self-gravitating systems heat up as they cool as a consequence of the negative heat capacity, and also in equilibrium thermodynamics this leads to instability. All right, we also saw by deriving the length, or rather the Jeans wave number, and combining the result with the virial theorem, that necessarily for a a stellar dynamical system or for a self-gravitating system, its size is comparable to the Jeans length, which contradicts the assumption of having a smooth background density that we can perturb. And this also shows that self-gravitating systems cannot be stable. All right, now this means that self-gravitating systems must be in a long-lived transient state. But as I said last time already, we have no principle at hand through which we could, for example, by maximizing entropy or so, find an equilibrium state for self-gravitating systems. The question as to what suitable concept for entropy could be for a self-gravitating system is still not answered. All right. Now, I would like to come to a different subject, namely to looking at disks. And the reason why this is necessary is, first of all, because disks are frequent in astrophysics. And disks are frequent because of angular momentum conservation. So angular momentum conservation leads to the existence of well-defined orbital planes. And in these orbital planes, also due to cooling mechanisms, material settles down, as we observe, for example, in protoplanetary disks, in accretion disks, in galactic disks, and so on. And so I would like to at least discuss simple properties of disks that we have to take into account if we look at astrophysical objects. Let me have a brief look at the stream. Things seem to be okay. Okay. All right, so now let me go to the board and begin with a discussion of disks. First of all, I would like to have a look at disk densities, so matter densities. And notice I'm talking about matter densities now, not number densities, because later I will study disks in the hydrodynamical limit rather than in the stellar dynamical approach, just because this will be much more simple than the stellar dynamical approach. All right. So what do we have to assume for the density of a disk? We have a density rho, matter density rho, that will depend on three coordinates, x, y, and z. And I'm going to assume later that x and y are the coordinates in the disk plane and z is the coordinate perpendicular to it. So this will be a surface density sigma of x and y and a delta distribution in z. In other words, there is a two-dimensional matter distribution which is confined to the plane z equals 0. Okay, now what does the Poisson equation tell us about this thing? So the Poisson equation says, as always, Nabla square phi is the disk potential, equals 4 pi g rho. But rho is 0 everywhere outside the xy plane, so we can say that this is 0 at z different from 0. All right, now what do we learn from that? The ansatz for the density that we have here suggests that we make a separation ansatz for the potential as well. So let's have a separation ansatz. Phi of x, y, and z is going to be psi of x and y times a function chi of z. That's the separation answers we make. And then I'm going to write the Laplacian, a two-dimensional Laplacian, let me write it like that, plus the second order derivative with respect to the z coordinate. Alright, now if I apply this Laplacian to this separation ansatz, you see that chi times the two-dimensional Laplacian applied to the psi function plus the psi function times the second order derivative of the chi function must be 0. And now, of course, you play the same trick as always with the separation ansatz. You say that, or you regroup this equation to say that minus chi double prime divided by chi equals something equals the two-dimensional Laplacian applied to psi divided by psi. Okay, now you have the usual situation that on the left-hand side and on the right-hand side you see functions that depend on different coordinates. Chi double prime over chi depends on z only, while the two-dimensional Laplacian applied to psi divided by psi depends on x and y only. And so this is only possible by setting both to the same constant, and I call this constant minus k squared. All right. Now, I have to switch the board here. Let's see how this works. All right, yes. Okay, now I'm going to use the first equation only for the moment. And I'm going to write this as chi double prime minus k squared chi equals 0. And so you see that this is an oscillator equation for the function chi of z. And this oscillator equation has a negative frequency squared. So the solution is going to be chi of z equals an exponential of plus or minus k times z. All right. So this obviously solves this equation. And now we need to see which of these two branches of the solution, which of these two independent solutions we need. So for z positive, if we are above the disk plane, the potential should decrease to 0 as z goes to infinity. So when I'm infinitely high above the disk potential should vanish. So for z positive, I need the negative branch, e to the minus kz. And by the same arguments for z negative below the plane, the disk potential should also vanish for minus z going to minus infinity. So in other words, below the disk plane we need the branch e to the plus kz. In other words, we can fix both situations at the same time by saying chi of z equals e to the minus k absolute value of z if we assume without loss of generality that k is positive. All right, so we've got that. And on the other hand, we still have this equation left, and we need to see what we do about that, but we are going to see this later. All right. This is a condition for solving the Poisson equation at z different from 0, so outside the disk plane. Now, of course, we need to relate the Poisson equation to the surface mass density and see how we can achieve that. And I'm covering part of the solution with the camera image, but okay, maybe that's possible. Okay. Now we need to establish the connection to the surface mass density sigma of x and y. And how are we doing how are we going to, I'm assuming that here is the disk somewhere, and I'm looking at some point within this disk. And I'm enclosing this point by a little box here, by a little, which is symmetric to the disk plane. So if I look at this situation here from the side, I have the disk plane here, so the z coordinate is here, and now I have enclosed my point of interest by this little cylindrical box. So it has an area dA, and this area is oriented along the z-axis on top, and it's oriented against the z-axis below. Right, because we have to take the exterior surface normal here, and it has a height h, like that, which I can shrink to 0 in the argument that is following. Okay, and now I'm using, for this little box, Gauss theorem. So I want to integrate over the box d3x nabla squared phi. I know from Gauss theorem that I can replace this by an integral over the complete area, the complete area surrounding the box. So this will be the boundary of the box, of the gradient of phi. Right? Gauss theorem tells me that I can replace the volume integral over divergence by the area integral over the argument of the divergence. And if I write the Laplacian as divergence of the gradient, you see this. Okay. But as I shrink the height of the box to 0, that part of the surface integral coming from the how to call this, coming from the part of the surface of the box that is not dA, not the bottom and the top, right? That will shrink to 0. So the complete integral will just be dA times the gradient of phi at z plus, right? This is a z coordinate at the top of the box, and I'm going to subtract dA times the gradient. The gradient of phi at the bottom of the box. Okay, and the rest of the surface of the box just doesn't matter. Now the gradient of phi will be projected on dA, so this will just be the absolute value on dA, because dA is pointing in the z direction. I only need the z component of the gradient at z plus minus dz phi at z minus. Okay. Now, since I know what the derivative of the potential with respect to z is going to be, at the positive side of the box surface, this is going to be minus k times the exponential function, which will follow. And at the bottom, it will be plus k, but this will be subtracted. And now I can take the limit of z going to 0 on both sides. So this will mean I will now take the limit of e to the power of minus kz for z to 0, and this is 1. Right, so this will go to 1, and this will end up in minus 2 dA times k. All right, and here I need to complete psi of x and y, right? Because the z derivative just does not act on psi of x and y. All right, so this is the statement from Gauss' theorem. And if I apply Gauss' theorem to the Poisson equation, and you may remember that this has a lot to do with looking at boundary conditions for electromagnetic fields, where one uses exactly the same trick with a little box that encloses the point of interest. All right, now let us complete this argument by asking what the Poisson equation says about this. Right, so I start again with the volume integral of nabla square phi over my little cylindrical box. By the Poisson equation, this will be the volume integral over the box of 4 pi g rho, of course. And rho will be sigma of x and y times the delta distribution as a function of z. Okay. Now if I reduce the volume to that little box I was looking at, the x and y integral will just turn into dA, and the z integral will integrate over this delta function, return 1. So we will get dA times 4 pi g times sigma of x and y. All right, and now we can compare these two results. Right? We have red is not a good idea here. Where am I? Here am I. Sorry, that's awkward now. How do I get my chalk back? All right. Let me take yellow chalk first. So we know from Gauss' theorem that this is true. We know from the Poisson equation that this is true. Now let us combine these two. Let's combine these two and conclude that psi of x and y, and we are going to need this relation later on, psi of x and y is 4 pi g divided by minus 2k, so this is minus 2 pi g divided by k times sigma, and now I say this is sigma k of x and y. Right, because this will now be the relation between, I call this psi k as well. This will now be the relation between the two-dimensional potential psi, the two-dimensional disk potential psi of x and y, and sigma k, right, for one fixed value of this constant k here. All right. Now here we have a relation for any value of this number k here, and we are assuming implicitly that k is positive without restriction of generality. Okay, so that's what we have now. Now, how do we construct a disk model from this? We can now, for each of the values k, linearly superpose, we can now, for each of the values k here, take the relation between sigma k and psi k. And first of all, construct a complete disk model by saying, all right, I'm going to linearly superpose with amplitudes s of k modes sigma k of x and y that I can then relate to a potential. All right. Now let us further restrict symmetry to saying that we will have cylindrically symmetric objects. Let me have a brief look at the stream. Things seem to be okay. All right. So let us restrict the situation to saying now we have cylindrical symmetry. And this means that I can write the two-dimensional Laplacian that I had above as 1 over s ds s ds. If s is the cylinder radius, right, something that we call rho earlier in the lecture, but now of course I need rho for the density, and therefore I'm replacing the cylindrical radius by s. Okay. So now I'm going to return under the assumption of cylindrical symmetry to this equation here, right, which relates the two-dimensional Laplacian of psi to this value minus k squared. All right. So if I can assume this, then I have 1 over s ds s ds applied to a potential psi, which is now only a function of s. And I need to assume that this is minus k squared times psi of s. Right? This is the specialization of one of our results of the separation ansatz that we made for the potential. All right. Now let us move on. I'm now going to write out this Laplacian. This gives me psi double prime, psi of s double prime, I should say, plus 1 over s psi prime of s is minus k squared psi of s. Now, let me introduce a new coordinate x, which is defined as k times s. And since these are these primes here denote derivatives with respect to s, I can write the same equation as some function psi of x with a double derivative taken times s squared. Now this will be plus s times am I doing this right now? 1 over s squared. This will also be 1 over I'm doing wrong here. Sorry. What I want to drive at is that by this coordinate substitution here, will turn into a Bessel differential equation. And its solutions are, well, it's Bessel's differential equation for functions f of x looks like this. It's plus x f prime of x plus x square minus nu square times f of x. All right, and here you see that if you make the substitution x equals ks in this equation here, and you replace the derivative with respect to s by a derivative with respect to x, you get Bessel's differential equation for order nu equals 0. All right, so we have a Bessel differential equation here for the Poisson equation, and this means that our solution psi of s is going to be a Bessel function a cylindrical Bessel function J0 of ks, or a cylindrical Bessel function y0 of ks. You see that the Bessel differential equation is a differential equation of second order, so it needs to have two different solutions, two linearly independent solutions. These are these Bessel functions J0 and Y0, Bessel functions of first and second order. Sorry, first and second kind. And since for s to 0, the Bessel function of the second kind, y0, goes to minus infinity, we cannot use that for physically models. So we know that the modes psi k of the potential can be represented by cylindrical Bessel functions of the first kind, j, and 0th order, j0 of k and s. All right, let me complete the k here, like that. Okay, so for any of the choices k that we made for our separation constant here, in our original separation ansatz, this one, we can find a mode for the cylindrical, or for the cylinder symmetrical disk potential psi k of s here. All right, so we know that we now can define potential modes phi k of s and z, which must look like j0 of ks, exponential of minus k, absolute value of z, and we must choose the whole thing negative in order, it must be 0, in order to satisfy the condition that the potential should be negative if we set its value at the boundaries of the region that we are looking at to 0. All right, and you see you are free to choose the sign here, because if psi is a solution of this Poisson equation here, then minus psi is also a solution. All right, so that's what we have here. And now let us return to this equation here that we previously had for the density modes. And you see, if you invert that equation, you see that we can write sigma of s now, due to the cylindrical symmetry. This is minus 1 over 2 pi g times k times what do we have here? Psi k. Psi k. Psi k of s. And the psi k of s is the Bessel function, right? So we can write this as minus k over 2 pi g times j0 of ks. And what we get in this way is, sorry, sigma k, the k mode of the surface mass density sigma here. All right, so this is what we now have established. And now we return to this equation here, this one, and get a complete solution for the sigma. So we say we can now write the complete sigma of s as an integral over some function s of k that I don't know yet. This will be for any positive number k, so I need to integrate over that. All right, now sorry, the psi must be negative here as well, and then we get a, what do we get? We get a positive sign here, and then I can compose the complete surface mass density by this expression. I'm going to write this a little bit differently. I'm going to take the 1 over g, the gravitational constant, out. I'm going to integrate from 0 to infinity over k dk divided by 2 pi s of k times j0 of ks. All right, this is an important equation now because it tells us how the complete surface mass density can be decomposed or can be constructed from individual Bessel modes, individual cylindrical Bessel modes. And we also know how these modes are related to the disk potential. All right, so far so good. Now, the same equation by a different route. Let's say I'm going to Fourier transform the surface mass density sigma s in 2 dimensions. Right, so what do I have to do? I will have to integrate over d2x over the complete 2-dimensional plane with a phase factor e to the minus I k times x. And the x is now a 2-dimensional coordinate. All right, this will be the Fourier transform of the surface mass density sigma of s. Now, I'm going to introduce, as before, plane polar coordinates. So I'm going to write the surface element d2x as s ds d phi. And d phi will be integrated from 0 to 2 pi, and s will be integrated from 0 to infinity. All right, sigma of s, which of course does not depend on phi, and now I have e to the minus I k s cosine of the angle phi between the vectors x and k. All right, now this looks awkward because we now have the trigonometric function, the cosine phi, in the face of this exponential. But now there's an important relation, an important integral that we can use here. I'm just regrouping the terms to separate their dependencies. Now I have the phi integral of the e to the minus I ks times cosine phi. This is 2 pi times, believe it or not, the cylindrical Bessel function j0 of ks. All right. And now you see that this means I started in the wrong way here. But this means that the same relation here, the integral over the cylindrical Bessel function here, is in fact a Fourier transform. Right? And this means that we can use the inverse Fourier transform to solve this expression here, to solve this equation for sigma of s for the function s of k. So this means that the function s of k is just the inverse Fourier transform of the surface mass density sigma of S. So this means this is the integral over S ds from 0 to infinity, sigma of S. Yeah, okay. Times 2 pi j0 of ks. Right, because if I do the backward Fourier transform, I just get this expression here. So now I can decompose, I can Fourier decompose the surface density sigma of S. And I see that this is exactly the same relation as we have it above, just because this equation here with a double line shows me that the complete surface mass density is just the Fourier transform of the function S of k. All right, now we can reassemble things in order to get the complete disk potential. Where do I have this equation? Yeah, you see, since the Poisson equation is linear, I can compose the complete potential psi of S also from the k modes of psi of S, so psi chi of S, psi k of S, times the function S of k. All right, so I can do that, and let me have a brief look here. All right, and now I can use the result that I had for S of k here. It's the inverse Fourier transform of sigma, and I can use the psi k of S are related to the Bessel modes. Right, so I'm going to use now, first of all, this expression here for the psi k of S. And I should directly aim at the complete potential here. All right, now I'm going to write 0 to infinity dk. Now, minus j0 of ks, which is coming from here. Now, times e to the minus kz. This is that. And now I need to complete the sk integral here. And this is now the integral from 0 to infinity. Now I need a different integration coordinate than I used here. I'm calling this x. So that's going to be x dx sigma of x now 2 pi times j0 of kx. All right, and now we have the desired relation between the disk potential, the gravitational potential of the disk, and the disk surface mass density. All right, this was the goal that I wanted to derive in the first part of this lecture today. And what it shows you is the following thing. Suppose you had been in 3 dimensions. Then, of course, you could have written down the Poisson equation in 3 dimensions. You could have taken the Poisson equation into Fourier space in 3 dimensions. And then you would see that you could assemble the potential just by Fourier modes, which are related to the Fourier modes of the density in 3 dimensions. And then you would have, instead of the Bessel functions J0 here, you would have the Fourier modes. So in other words, what this equation here tells you is how you can, in a way, very similar to a Fourier transform. In fact, by a Fourier transform in 2 dimensions, assemble the 3-dimensional disk potential phi of S and Z, it should be. Not by using the Fourier modes, e to the plus or minus ikx, but by the cylindrical Bessel functions J0 here. That's the main aspect of this whole consideration here, to show how the surface mass density is related to the disk potential in a way that replaces the 3-dimensional Fourier transform essentially by a 2-dimensional Fourier transform. All right, that was what I wanted to show in the first part of the lecture today. And now let us take a brief break, and then we are going to continue with a stability analysis of disks, which will lead to the so-called Toomre stability criterion. All right, so see you again in about 5 minutes. So, can we continue? I'm a little bit afraid that the stream will be interrupted if it's not active. Therefore, I think we should continue now. So, why did we do all that? I mean, the main result of the previous section of the lecture of the past 1 hour approximately was to establish a relation between two-dimensional mass distributions and a three-dimensional gravitational potential. That was the point. Now, why did we do that? That was also because for any stellar dynamical model, we need the gradient of the potential in order to solve Liouville's equation. And now we have at hand a relation that allows you to construct a gravitational potential for any two-dimensional mass distribution, for any surface mass density. You find in the theoretical astrophysics book an example with a so-called Maclaurin disk that will fall off to 0 within a certain radius in a way that depends on the square root of essentially 1 minus x squared. All right, that is just an example there. Now, let us come to something different, namely to a stability analysis of disks. And this is important because you see unstable disks everywhere in astrophysics. For example, right, the spiral arms of a spiral galaxy, they signal instabilities against disk fragmentation. In protoplanetary disks, in accretion disks, for example, it's important to know under which conditions will a disk remain stable and not fragment. In other words, we would again like to do a stability analysis. And we are going to follow the same recipe that we always follow with stability analysis, namely, we first collect the relevant equations, decompose the solution into a background solution and a perturbation, linearize the relevant equation in the perturbations, and then decompose the perturbations into plane waves. Now, of course, the difference to everything that we did previously is that we now have to do with an essentially two-dimensional system. And there are some difficulties that we have to deal with. In addition, we will have to take into account that we now have a two-dimensional system that will be stabilized only by its rotation. And we are going to transfer into a co-moving frame, co-moving with the rotation of the disk. And this will mean that we will then lose, we will then escape from an inertial system. We will move from an inertial system to a non-inertial system. And therefore we will have to explicitly take into account that we have non-inertial forces then. And the two non-inertial forces that appear are the centrifugal force and the Coriolis force that we will have to take into account in addition to the other forces that already appear in the equations that we have. But which equations do we choose? I mean, we want to have to do with stellar dynamical systems. And the whole analysis becomes rather complicated in stellar dynamics. So I will move to the fluid approximation just because we saw that in a collisionless stellar dynamical system, the Euler equation is replaced by the Jeans equation. The continuity equation will remain the same. So the macroscopic equations that we are dealing with will be the same as in fluid dynamics, and we will do the analysis as in fluid dynamics. All right. So let me go to the board. We have to do with the stability of disks now. And we are going to use the continuity equation. and the Euler equation. And let me write the density over here. So we would here have the gradient of the pressure. We would have here the density times the gradient of the gravitational potential. So this would be Euler's equation as you know it, but now we move to a non-inertial system, and this is why we have to add the Coriolis force. Sorry, that's -2 times omega. That's the angular frequency of the rotation of the system. Here's the velocity, and we will have the centrifugal force omega squared times x. All right, so these are the non-inertial force terms. Okay, now we have to deal with that. All right. We have a two-dimensional situation. And therefore, the gradient, the velocity are two-dimensional. Well, I should first of all restrict this to the velocity only. All right. But then you see the divergence here. The divergence that appears in the continuity equation will not have a z component. And this is why I can directly integrate the continuity equation along the z-axis. And then this will lead to a continuity equation in two dimensions, which reads dt sigma, that's the surface mass density, plus now the two-dimensional divergence applied to sigma v and not to rho v. All right, this is the first of our relevant equations, the continuity equation in two dimensions. All right, in the Euler equation, I will take into account here that the velocity only has x and y components, and therefore I will also consider the x and y components of the gradients on the right hand side only. But then again, I can integrate the Euler equation also along the z-axis. Well, this means then that this factor rho here on the left-hand side of the Euler equation will turn into a sigma. All right, and this means that the Euler equation will turn into dTv plus v times gradient times v equals minus gradient p over sigma. The same will happen to this row here. So this, if I divide then by the sigma that I get after integrating the density over z, will mean that this prefactor here will drop out, and minus gradient phi remains. All right, and this factor of rho also applies to the non-inertial force terms. Wait a moment. This is now getting a bit tricky here, because I need to take the minus signs into account. All right, now I have -2 times omega cross v plus omega square times x. All right, so the only change that you see in comparison to the Euler equation as you know it is that instead of the density we divide by the surface density here, and that we have these two non-inertial force terms on the right hand side. Okay. This is the second relevant equation that we have to take into account. What else do we need? Of course, we need the Poisson equation, and we are going to use it in a way as we derived it earlier, so we do not worry about this at the moment. But now we are in a co-rotating frame, in a frame that is moving with the rotation of the disk. And first of all, we say that the rotation is perpendicular to the disk plane. Omega vector equals omega absolute times the unit vector in z direction. This will also mean that the components of the Coriolis force will fall into the disk plane, of course. And if we now introduce in the usual way a background velocity or rest velocity v0 and a perturbation dv, this means that v0 equals 0 because we are already in the co-moving frame. In the frame moving with the disk, v0 will of course be 0. So as we now move on to a perturbative analysis, we can replace the velocities by the velocity perturbations, delta v. All right, now what do we have? We have our relevant equations. Now we do the decomposition of sigma into background plus delta sigma, of velocity goes to delta v only. And of course, we also need to take into account that the gravitational potential will be composed of the gravitational potential of the unperturbed disk, sigma 0, plus a potential fluctuation, delta phi. That's what we have. Now, if I apply Euler's equation to the unperturbed background solution, the left-hand side of Euler's equation here will be 0 because our background velocity will be 0 because we are in the co-moving frame. But then the disk surface density will be constant, sigma 0. So the gradient of the pressure will also be 0, because we will assume, like we did in three-dimensional hydrodynamics, that the pressure is a function of the surface density only, and if the surface density is constant, then the pressure will also be constant. You know, in three-dimensional hydrodynamics, we had pressure is a function of density, P of rho. Now we have P of sigma. All right, so the gradient vanishes, and on the right-hand side, the only thing that we will have left is gradient phi 0. Velocity is 0, so the Coriolis term also vanishes, and then we have plus omega square times x. And this is a very interesting thing, because it shows you that the gradient of phi 0 must be omega square times x. Now have a look at this. We have a planar situation, right? We have a surface mass density only, and we have assumed the sigma 0 to be constant. But then the gradient of the potential phi 0 must point along the z-axis. Right? But the centrifugal force term, omega squared times x, it cannot point along the z-axis, right? Because x falls into the xy plane, right? So this is proportional, or let's put it in this way. This is going to be perpendicular to Ez. So what this shows you is that there is no such situation unless the disk that we are speculating about, the disk with the surface mass density sigma 0, is embedded into an object that can stabilize it against the centrifugal force. For example, the surrounding mass distribution of the galaxy, or a larger system that embeds a protoplanetary disk or an accretion disk and so on. Right, so this shows you that you need to embed the background solution, the disk with the surface mass density sigma 0, into a larger three-dimensional object if that is to be stabilized against the centrifugal force. Okay, but let us now return to a perturbative, to a linearization of our relevant equations in order to arrive at a perturbative solution. So, if I write the continuity equation at first order, right, so I'm taking away the 0th order terms and I'm looking at these terms at first order only, then I have the time derivative of the surface mass density fluctuation plus sigma 0 times the divergence of the velocity fluctuation. Right? Because we are in the co-moving coordinate system, co-moving with a disk, the background velocity v is 0. So there is only a first order contribution to the velocity. So in order to arrive at the first order term in the continuity equation, I need to multiply this with a 0th order term only of the surface mass density. So that's sigma 0 times the divergence of delta V. So this must be 0. That's the linearized continuity equation. The linearized Euler equation, first of all, starts with the time derivative of the velocity perturbation. And then by the same arguments that we usually made in three-dimensional hydrodynamics, the term v times nabla applied to v at first order vanishes altogether, right? Because for the vanishing background velocity v0, the term v times nabla times v would be second order directly. Okay, so the left-hand side is done. Now on the right-hand side, I have to use the gradient of the pressure fluctuation and have to divide this by sigma 0. Now I'm doing that because the pressure cannot have a non-vanishing gradient for the background solution. Gradient of P0 must be 0. So there is only one contribution to the first order perturbed pressure gradient, that's gradient of delta P. But since this is already of first order, I need to divide here by the 0th order of the surface density. F minus the gradient of the potential fluctuation. And then you see, since the 0th order solution must also be satisfied, the gradient, I can subtract the 0th order solution from the first order solution, and this will cancel the gradient of the background or the unperturbed potential phi 0 against the centrifugal force. So this will be gone, and the only term that will remain is minus 2 times the vector product of omega with the velocity perturbation here, which is the Coriolis force applied to the velocity perturbation. All right, this is now our linearized system. It's not quite complete yet, because if I take the gradient of the pressure fluctuations, this is going to be the derivative of the pressure perturbation with respect to the surface density times the gradient of the surface density fluctuations. Now this, as in ordinary three-dimensional hydrodynamics, I call the sound speed squared. Right, in this way I can replace the gradient of the pressure perturbation by a gradient of the surface density perturbation. And now I'm going to use a relation that we had before. No, I should introduce this only when we have decomposed the fields into Fourier modes. All right. So with that, I'm getting dt delta sigma plus, well, it's going to be the same equation as above. Right? Let me take this away, and let me only notice that this term here is going to be replaced by cs square gradient delta sigma divided by sigma 0. All right, and now we are going to decompose the perturbations into Fourier modes, into plane waves. So let me go to a new page here. And now, first of all, write the continuity equation in Fourier modes. That's going to be minus I omega delta sigma. Again, using the same symbols for the Fourier amplitudes or the plane wave amplitudes as I did for the configurations in real space. All right, now plus I k times delta v times sigma 0. That's 0. All right, then for the Euler equation, I get minus I omega delta v. And remember, delta v only has components in x and y direction, so these are two equations only. Now, on the right-hand side, I get I times cs squared vector k times delta sigma divided by sigma 0. And again, of course, since we are decomposing two-dimensional perturbations into plane waves, the vector k will have a kx and ky component only. All right, now we have minus ik delta phi, and here we have now the Fourier modes of delta phi. That's important for what we are going to do soon. All right, and here we have minus 2 times omega vector product with delta v, and notice that the vector delta v here, or the Coriolis, the complete Coriolis term, has no factor I. This is important for moving on. And now I'm going to use a relation that we had way above, namely that we can write the Fourier, or that we can relate the Fourier modes of the potential with the Fourier modes of the surface density by minus 2 pi g over k times delta sigma. Do you remember that? We had this relation way above, and it's this relation here. Okay? So I'm going to use that here. And this will allow me, of course, to replace or substitute for delta phi in this way, so that the only variables that we have to deal with are now delta sigma, delta vx, delta vy. So we have 3 variables, and all the rest will be gone. All right, now I'm going to do a further thing, namely I'm going to orient the xy coordinate system such that the wave vector k of the perturbation, of the plane wave perturbation that we have decomposed these equations into, that this k will point into the x direction. So I'm going to take the liberty to orient the x-axis with the vector k. So I'm assuming that k is k times ex, and this means that ky is 0 and kx equals k. Okay, under this further choice of symmetry, let's say, I can write the continuity equation as omega times delta sigma. So I'm cancelling out the factor minus I here. Then minus k delta Vx times sigma 0 equals 0. Okay, nice. Next thing. Here I have omega delta Vx if I focus on the x component for now. Now I need to divide by minus I, so this will be minus cs squared k delta sigma divided by sigma 0. That's this term. I have divided by minus I, so that's going to be plus k delta phi. But I know what the delta phi is. Right? I'm taking delta phi from the Poisson equation. So that's going to change into a minus sign, minus k times. But the k is going to cancel. Nice. So that's minus 2 pi g times delta sigma. Okay. So that's this term here. All right, and now I need to divide by minus I. So that's going to be plus 2 over I or minus 2I. And now I need the x component of the Coriolis force. I need a little calculation on the side here. So omega vector product with delta Vx equals omega absolute times Ez, vector product taken with delta Vx Ex plus delta Vy Ey. So this is omega, now Ez, vector product with Ex is Ey. So that's going to be delta Vx Ey. And here we have Ez, vector product with Ey, that is minus Ex. So that's minus delta Vy times Ex. All right, now here I need the x component of that. So this is plus omega delta Vy. All right, now this is the x component of the Euler equation. All right, now for the y component of the Euler equation, I get omega times delta Vy equals, the first term on the right-hand side does not have a y component because we oriented the coordinate system such that ky equals 0. All right, so this is going to go away. Again, here, same argument holds, right? Ky is 0, so the next term, the potential gradient, also does not have a y component. So the only thing that remains is divided by minus I. So that's plus 2 over I, or minus 2I. And now the y component of the Coriolis force, this is omega times delta Vx. All right. So these are the equations as we have them now. Now I need to regroup them a little bit because of course we want to rewrite them in matrix form and use this vector here as the vector of unknowns. So if I write the whole system of equations in matrix form, I'm getting omega times delta sigma from the continuity equation. Then I have a minus k times sigma 0 times Vx, delta Vx, and I have no contribution from delta Vy. Okay, now did I make a sign error here? Yes, I did. Yeah. Look, the potential, the pressure gradient must have a negative sign. So this means that this term must also have a negative sign. And since I divided by minus I in order to get here, there must be a positive sign here. All right, and now I'm going to bring this on the other side in order to write the x component of the Euler equation in the form something equals 0. So I need to bring this on the other side. If I do that, then I have 2 pi g from the potential gradient minus k cs squared divided by sigma 0 times delta sigma. Now that's going to be a bit crowded here, so let me make more space. All right, so this will be the factor multiplied with delta sigma in the x component of the Euler equation. These are these two terms, right? This one and that one, except for the delta sigma. Okay, now we need the factor multiplying delta Vx, that's this omega here, from that term. And then for the Vy, delta Vy, we get a minus 2I omega. Okay, and finally, in the last equation, there is no contribution from delta sigma. There's a plus 2I omega for delta Vx, and there is an omega for delta Vy. So this means that we can represent the three above equations with a double line here in the following way. We have the vector delta sigma, delta Vx, delta Vy, these are our unknowns, times this matrix here that we just constructed must be 0. And now, of course, we have the same situation as always, right? In order for our perturbations to be non-trivial, to be non-zero, the determinant of this matrix must vanish. And we get a dispersion relation as always. So the determinant of this matrix must be 0. Now let's calculate the determinant. That's going to be omega times the determinant of this 2 by 2 submatrix. That's omega squared. Now minus 4I square omega squared. So that's minus 4 omega squared. Right? We have, if we multiply these two together, we get plus 4 omega squared. We need to subtract this, we get a minus sign. All right, then we have plus k sigma 0 multiplied with the subdeterminant of, minus k cs squared divided by sigma 0 times omega. And that's it. That must be 0, right? So this is the determinant of the, if that was matrix here and calculate its determinant, it's not difficult. All right, so this must be 0. This is our dispersion relation for disk stability. All right, so you see from there that either omega equals 0, that's a boring solution, right? This is a solution that, that is static, a static perturbation. Omega equals 0, okay, or omega squared equals 4 capital omega squared minus, well, let's take the positive solution first. This is k squared c squared, right? That's the product of these two. And then we have minus 2 pi g k sigma 0. This is our dispersion relation, right? The interesting part of the dispersion relation for disk stability. Now you see, okay, suppose we set omega equals 0 in the first place. That could be a very slowly rotating disk. Under this condition, we can directly say omega square equals k square c square minus 2 pi g k sigma 0. All right, fine. Now, we know that at the boundary line between stability and instability, omega equals 0. And then the wave number has the meaning of a Jeans wave number. And this leads to kj equals 2 pi g sigma 0 divided by cs squared. This is what is usually called the Jeans wave number for disk stability. All right, again, we go to the limit of a very slowly rotating disk. We go to the boundary line between stability and instability with a small omega equals 0 as well. And this leads to the Jeans wave number. Separating between stability and instability. Okay, now, you see that if you return to the complete dispersion relation here, omega square is 4 capital omega square plus k square cs square minus 2 pi g k sigma 0. You see from there that omega square can be positive and negative. Now let us search for the condition under which the complete disk will be stable. All right, so this means that for all wave numbers, omega square must be positive. But you see, this is a parabola in k square here. Right, so we search for the minimum of that parabola and ask, when is that minimum not negative? And then we will know whether the complete disk will be stable. So let us see where d omega square with respect to dk equals 0. So this will be the minimum that omega square will have, because the parabola is open, opens upward. Right? So this is 2k cs squared minus 2 pi g sigma 0. If this is to be 0, then k must be pi g sigma 0 divided by cs squared. And you see, this is just the Jeans wave number divided by 2. So this is where the minimum of omega is going to be. And now we demand that this omega square that we have obtained in this way, let us call this k0. Let us call the corresponding omega 0. Then we have that this is 4 times omega squared plus k0 squared times cs squared minus 2 pi g k0 sigma 0. And in the logic of what we did, we will demand that this should be larger or equal than 0, because then the minimum of the omega square in our dispersion relation is going to be non-negative. And this means that omega square everywhere for all wave numbers will be non-negative, and then this means that this implies that the disk will be complete. All right, now let us insert finally the k0 square that we have just derived. Then we get that 4 omega squared plus, okay, now the k0 squared. So this is pi g sigma 0 squared. And now we have cs squared in the denominator and cs squared in the numerator, so we have divided by cs squared here. Okay, fine. Of that we have to subtract 2 pi g sigma 0 times k0. Right? So again, we'll get 2. Now pi g sigma 0, this is the numerator of, so also here we will have pi g k0 squared divided by cs squared. Right? This must be larger or equal than 0. So you see, we have two terms of the same shape, and we find 4 omega squared must be larger or equal pi g sigma 0 divided by that squared divided by cs squared. And you can turn this into a simple criterion. If you take the square root of both sides and use the monotonicity of the square root, then we have omega cs divided by g sigma 0. Right, these are all the quantities, the physical quantities that appear here, must be larger or equal pi divided by 2. This is an important criterion. This is called Thumres criterion. Thumres criterion. Okay, named after the two brothers Thumre who divided this. Who derived this. And as we derived it, you see that this is a criterion for disk stability. This is very interesting because it tells you that, first of all, the sound speed and the disk rotation stabilize the disk, right? Because the larger omega is, the larger cs is, the larger is the numerator here. And gravity, gravity appearing through g times sigma 0, destabilizes the disk. Right? So this is exactly the balance that you would expect. Right? The rotation stabilizes the disk, gravity destabilizes the disk. Okay, this was the goal for the second part of today's lecture, namely to derive Thumres criterion. So we had two parts of the lecture today. The first one was, how do we construct a potential, a gravitational potential for a two-dimensional mass distribution for a disk? And we saw that we can do this in a way very similar to a Fourier decomposition of the disk, except that the Fourier modes that we have to take into account are not the usual plane wave Fourier modes, but the cylindrical Bessel functions of first kind and zeroth order, the J0 functions. That was number one. Number two was the derivation of a stability criterion for disks. And we did this in the fluid approximation. We found that Thumres criterion then looks like omega cs divided by g sigma 0 is larger than pi over 2. That's 1.57 or something. And if you do this in stellar dynamics, you find a little bit larger value, around 1.6 or so. But nonetheless, the idea is the same and the numerical value is very close. All right. This was everything that I wanted to show today. Sorry for the circumstances. Next Monday, the lecture will continue as usual in the lecture hall, I hope. And then next week will be the last week for this term where we will discuss new material. And what I wanted to do next week is, first of all, talk about Chandrasekhar's equation for dynamical friction, which is very important because it is a friction process that necessarily occurs in. And then maybe if some time is left of the lecture times next week, I could maybe briefly talk about the Fokker-Planck approximation, which will be an approximation including collision terms in our initial Boltzmann equation. All right, let's see how far we get. So much for today. Thank you very much for your attention, and see you hopefully in presence again in the lecture hall next Monday. Thank you and goodbye.